All right, let's jump right in. Today, we are demystifying the tech that is absolutely everywhere right now, large language models, or as you probably know them, LLMs. We're going to break down what they are, how they actually work, and, where this is all headed. So here's the game plan. We'll start with the absolute basics. Then we'll get into the one breakthrough that really changed everything. After that, we'll look at the recipe for building one of these things, weigh their incredible powers against some serious flaws, and finally, we'll zoom out and look at the future we're all building with this tech. First up, what even is a large language model? You hear the term thrown around constantly, but what are you really talking about? It's way more than just a fancy autocomplete. At its absolute core, an LLM has one simple goal: predict the next word in a sentence. That's it. But, and this is the magic part, when you train it on a massive, massive chunk of the internet, it starts to do more than just predict words. It starts to pick up on grammar, facts, reasoning, and even concepts about our world, just from the patterns in the text. And this quote from Microsoft Research just nails the central debate, right? When a model like GPT-4 can ace exams for things like law, medicine, and coding, well, it really forces us to ask what we even mean by words like intelligence or understanding. So how in the world did we get here so fast? I mean, the leap from those clunky old translation websites to the AI we have today wasn't a slow, gradual thing. It was a seismic shift, and it's all thanks to one brilliant, revolutionary idea. For decades, progress was pretty steady. We had statistical models, then we moved to early neural networks, but then 2017 happened. A paper from Google researchers called Attention is All You Need introduced something called the transformer architecture. And it didn't just move the goalposts, it completely changed the game. So what was the secret sauce? It was a mechanism called attention. See, before this, models had to process text one word at a time, in order. That made it really hard for them to remember what was said at the beginning of a long paragraph. Attention fixed that, completely. What this means in practice is that the model can look at an entire sentence or even a whole document all at once. It figures out how every word relates to every other word. So in a sentence like "the dog, which had been chasing squirrels all morning, was finally tired," the model knows "was tired" refers to the dog, not the squirrels, because attention lets it see the whole picture. Okay, so we've got the architecture, but what does it actually take to build one of these things? Well, it turns out the recipe is kinda simple, but each ingredient is just monumental. You need three things, and they all have to be huge. First, a massive data set. We're talking a significant slice of the entire internet. Second, a massive model, a neural network with billions of little knobs to tune called parameters. And third, a truly massive amount of computer power to put it all together. And just to give you a sense of scale, Google's Palm model has 540 billion of those parameters. Think of each one as a tiny connection in the model's brain that gets fine-tuned during training to capture another little pattern in language. As you can imagine, training a model that big is not cheap. The cost for Palm was estimated to be around $8 million. That's because it requires these giant, specialized data centers running at full tilt for weeks, sometimes months on end. The training itself happens in two big phases. First is pre-training. This is where the model just reads pretty much the whole internet to learn language and facts. But that raw model can be a little wild. So then comes phase two, fine-tuning. This is where human trainers actually teach the model how to be helpful, honest, and safe, using a process called reinforcement learning from human feedback. So what happens when you mix all that data, scale, and training together? Well, you get something with absolutely incredible abilities, but also some really frustrating and persistent flaws. It is a classic double-edged sword. And this right here is the fundamental tension of today's LLMs. On one side, they develop what researchers call emergent abilities, skills like reasoning that we never explicitly program them to do. But on the other side, they have major problems like hallucinations, which is a fancy word for making stuff up, and they can soak up and amplify all the biases from their training data. And look, these aren't just little bugs. These are fundamental challenges for the whole field. Hallucinations destroy trust. Bias can cause real-world harm. And security holes mean they can be tricked into ignoring their own safety rules. Solving these issues is the #1 priority for researchers right now. So, with all these amazing powers and these very real dangers, what does it all mean for us? Well, this isn't a science experiment anymore. This technology is already out in the world, and it's starting to reshape our entire society.
The economic numbers are just staggering. A report from Goldman Sachs estimated that generative AI could eventually boost the annual global GDP by 7%. I mean, that is trillions of dollars in new economic value. It's hard to even wrap your head around that.
But that economic boom comes with a massive, massive shift in the workforce. That same report figured that 300 million jobs could be exposed to automation. Now, the key here isn't just about jobs disappearing, it's about the very nature of work itself changing for almost everyone. And that leaves us with this final, really important question. We're building systems that don't just follow instructions anymore. They can write, they can code, they can reason. They're becoming less like tools and more like agents. So the question isn't just what can we do with them anymore, it's how are we going to collaborate with them? And that is a question that all of us are going to be answering together in the coming years.